Hello, everybody. Welcome back. In this lesson, we will go over the first layer of applications of the derivative. Now, when it comes to applications of differentiation, you can find a variety of applications leading towards theoretical problems as well as real-world applications. Now, this in this particular lesson, we will go over a specific topic called related rates, which essentially talks about relating different variables and talking about their rates of change. So this particular topic is in fact like the ground level of applications of the derivative, because it is not demanding any uh, um, complex or complicated sophisticated tools. Instead, it is just about like relating variables via basic uh, relations, geometric or otherwise relations that we can figure out easily. So without a further ado, let's get to the main task here. First of all, when you look at any related rates problem, first of all, these are word problems. So usually when it comes to this kind of problem, read the question, understand the problem, draw a diagram to figure out to have a better understanding of the scenario, and then introduce variables. And once you're through that level, now you, after that step, you can recognize the connection between variables and most probably writing down an equation that would connect the components, or it could be um, some kind of a connection, right? So after that particular point, it is just about differentiating that equation or differentiating that relation. So that's exactly uh, the practice, and I will show you what I mean by an example. So example number one, the radius of a circular disc is increasing at a rate of 1 centimeter per minute. What is the rate of change of the area of the disc when the radius of the disc is 12 centimeters? So they're asking for the rate of change of the area at a particular moment, exactly when the disk is at the radius of 12 centimeters. Now, to talk about this, first of all, this is about a circular disk. So let me draw a circle. And of course, it's a disk that has a thickness, but it is not exactly the concern here because we're considering just the area. Now, the area and the radius, we have these two variables in this picture, the radius and the area. And if we write down the area, it's none other than the famous connection, right? So pi r square. Now, that is the connection between the area and the radius. And then let's try to mathematically write down the given information. The radius of the circular disk is increasing at this rate. That simply means if you consider dr dt, because we know the rate of change is none other than the derivative. So here you consider the derivative and the independent variable is time, that we can figure out from the context. So dr dt, the rate of change of the radius, rate of increase of the radius. So by any chance, if it says like in a certain occasion, like instead of having increasing, if it is saying decrease, then we may need to have a negative sign in front in this situation. But now in this scenario, we will have just 1, and of course centimeters per minute. I will just indicate it here. But as far as we are consistent with our units, we do not need to pay too much attention into those. Now the rate of change of the radius is given right there. Now our question is figuring out dA dt. That is our question. Find the rate of change of the area. That's what we need. So now this is easy. Grab this relation, differentiate. So since you have a equals pi r square, now it's just about taking the derivative with respect to variable t, because that's our underlying variable. On the left side, it's dA dt in simple words. In the right side, pi is a constant which can be pulled out. And then when you differentiate r square with respect to t, now here there's a mismatch of variables. That's exactly when we would employ the chain rule. So first differentiate with respect to r, so that becomes 2r, and then dr dt. This is the first layer of the chain rule, and this is the second layer of the chain rule for the inner function. Now, given this surrounding, what we need is the dA dt. We need to find the radius. We need to find the rate of change of the area when the radius is particularly 12 centimeters. Now, I would say we need dA dt when r equals 12. So I will indicate it by the symbol. That's exactly what I'm going to compute. So on the right side, I do have 2 pi, and then r is none other than exactly this value on that occasion. So it's going to be 12 times dr dt is none other than just 1. So 1. So which turns out to be 24 pi. So 24 pi, and you can say if you would like to have the units, it's nothing other than square centimeters per minute, because square, it's a square measure with respect to time. So it is that simple. It's just about having the relationship, having the corresponding relationship between the variables, and then differentiate it to connect the derivatives with the picture. All right, so let's proceed to the second example. In this occasion, since it's a similar example, and henceforth I will just provide you the work and I will explain. I already have the answers prepared. So the first one, a circular metal disc on heating engine expands its area at a rate of 0.2 square centimeters per second, at which rate the radius is increasing at the moment it has radius of 3 centimeters. Now, if you look at this very carefully, this is exactly the same problem flipped the other way around. You are given the rate of change of the area, and what we need to figure out is the rate of change of the radius. The same relation, so it's not going to be challenging. It is exactly figuring out dr dt, and we need to work backwards. We need to divide both sides by this, and then when you do that, don't forget we need to have r exactly the value that you consider in this particular moment, that is 3 centimeters. So that will result the radius, the rate of change of the radius is none other than 0.1 divided by 3 pi centimeters per second. And in this occasion, you do not need to simplify any further. Just it's the answer. It's a final answer. Now let's proceed to another example. Let's read the context. A 6 feet tall person walks at a rate of 3 feet per second away from a light that is about 15 feet above the ground. At what rate is the tip of his shadow moving when he's 7 feet away from the base of the light? Now, in this kind of scenario, you need to draw a picture, first of all, to identify what's going on. First of all, the picture. There's a light pole, and of course, the light is located 15 feet above, and the person is 6 feet tall, and the person is moving away from the light. Now, the person is moving away from the light pole, uh, from the bottom of that light pole. It's the speed is given. It's 3 feet per second. The speed of the person is provided. Now the question is, what's happening with this tip? When you consider right here, when you consider the tip of the shadow, how fast the tip of the shadow moving away, we all can guess it's moving away from the light source, but how fast is moving away? To understand the scenario, first of all, now you can have some guess right at the beginning. Since the person is moving 3 feet per second, why shouldn't we have the same speed for uh, the shadow? Now, if you have the same suspicion, think about this scenario. Think about this or try it and see how it would work. Like when you walk away from a light, is your shadow moving at the same speed? All right, so let's figure it out. Now, the next step is, first of all, once we have this, now this is a concrete picture of the scenario, that is a concrete application. However, sometimes it could be overwhelming with some unnecessary information. Here I drew the person, here I drew the light bulb. I mean, all of these are fine, but we need to figure out the abstract picture, abstract mathematical picture in the application. That is exactly the abstract nature of mathematics. We need to recognize, after removing all the dust and the rust from the description, we need to recognize the pure mathematical picture. That mathematical picture is none other than exactly this triangle. And not only one triangle, there are two triangles involved with this. One triangle with the height of the person, the other triangle with the height of the light pole. Now, with this, we immediately indicate one of the variables, that is the position of the person, variable x, the distance to the person starting from the base of the pole. And then again, we need to play with the other component. We need to see how fast this point is moving away from the light pole, or like the base of the light pole. To recognize it, we will have another variable employed, right? Variable y, to indicate that. Now, when you do that, these are the things that we know. The rate of change of variable x, that is exactly how fast the person is moving away. So that is 3 feet per second. The question that we need to figure out, or the quantity that we need to figure out, is dy dt, which is essentially how fast this tip is moving away from the base. Now, to work with this, first of all, since we have this triangle inside another triangle, in other words, it is the situation of a similar triangles, right? We have proportionality in this picture. So what we need to do is to have the base to height ratio on both scenarios, on both triangles. So base to height. If you consider the small triangle right here, the base is y minus x. Based on these variables, you can see y minus x is going to be exactly the length of the base here, and then the height is none other than 6. So y minus x divided by 6. That is that ratio, which is none other than the ratio of the base of the large triangle to the height. So that is going to be y divided by 15. And then this is the connection that we have. That's the connection. And once we have that connection, what we need to do in the next step is to come up with an equation combining x and y. Now we do have that equation, but let's just clean it up a little bit. So cross multiply, you can simply cross multiply by using these fractions. Nobody likes to work with fractions unless it's unavoidable, right? So cross multiply, and this is what you're going to end up getting. And once you have it, gather like terms on one side, and you will end up getting 9y equals 15x. And once you have it, now at this point, you can take the derivative. If you take the derivative directly, it says dy dt, with respect to time, the rate of change of quantity y, and then the rate of change of x with respect to time. So once we have these two, now don't forget, our question is concerning dy dt. So all you need to do is to play with this equation. So dy dt is supposed to be just divide by this, and then writing it separately, why don't we just follow exactly what we have here? It's 15 divided by 9. And then don't forget, when you plug in the value, the corresponding value for dx dt, you end up getting just 3 right here, and then there will be a cancellation. So that would be 5 feet per second. Now, this is understandable. Look at this. This person is moving away from the light pole at a certain speed, and the tip of the shadow is always ahead, and it will move faster than the person. So interesting observation. If you have not experienced this, I recommend you to see how it works. Walk away from a light and see whether your shadow is moving away at the same speed or is it at a different speed. All right, so the next scenario. I do have that scenario also prepared, so why shouldn't we have it, first of all, as a reading before seeing an illustration? Two boats leave a port at the same time. One travels west at 20 miles per hour, and the other one travels north at 15 miles per hour. At what rate the distance between them is increasing after 30 minutes of departure? Now, to understand this, now think about this. One travels north, the other person travels west. But the same thing sometimes by mistake, if you put it like this, other than saying west, if you have east, if you put it in the picture, don't just bother erasing it, because it's just the same picture. It is like almost symmetric. At the end of the day, you need to figure out the rate of change of the distance between them, right? In other words, it's asking you to find the relative speed between these two boards. What is the relative speed? Relative speed simply means if you observe one board from the other, how fast the other board is moving away from your board. That's exactly the relative speed. So now, to identify this scenario, why don't we go ahead and have it with our description, with the picture. Starting step, just draw step as a starting step. Just draw a triangle, and here in this case, I marked it like moving towards east. It doesn't really change anything in the final answer. So for convenience, I put it towards east, and that is board A. It's going towards east at a speed of 20 miles per hour, and board B is heading towards north at a speed of 15 miles per hour. And then the connection between these two. Now, of course, we need to measure the speeds. To do that, I indicate this length from O to A. O is none other than the port. So that distance, it is indicated by X. And then the port to point B, it is indicated by variable Y. Now, in that case, we know immediately dx dt and dy dt. These two are the speeds of the corresponding boats. And then what we need to figure out is how fast, or the rate of increase of the distance between these two boats, which is none other than represented by z. So now, what is the connection between these? Z square is none other than x square plus y square. Of course, consider this picture on a small scale. If you consider this on global scale on the earth, this may not work that nicely, because the Pythagorean theorem is exactly demanding a right triangle. But if you lay a huge right triangle on the surface of the earth, it need not to have 90-degree angle between. That is a different aspect, because this is not, I mean, in that scenario, you're not going to be on plane geometry. It is a different scenario. However, we consider we are not overcomplicating any of this. So those are the assumptions in mathematical modeling. So this is a mathematical model. So in this scenario, what we do is exactly starting from this equation, right? Now we're trying to prepare the rate of change. So take the derivative. When you take the derivative, we employ the chain rule in each scenario. So with respect to z, it is 2z and dz dt. And here 2x dx dt, 2y, and then dy dt. And then don't forget, this factor 2 is a common factor to all of them. You can cancel it right away. And then what you need to figure out is dy dt. Now to figure it out, what you can do is, right, this is what we need. To do that, to find it, divide both sides by z. And then you end up getting this formula. Now, let's try to figure out if we have all the information on our hand. When you consider dx dt, it is already given. So that is 20. It is right here. Dy dt is given. It's right here. And then you need to figure out x, y, and z. But x is none other than, when you consider 30 minutes, now this is a situation where you need to be careful with the units. All the speeds are given in terms of miles per hour, and I'm asking you to think about the situation where after 30 minutes, when 30 minutes, after the pass of 30 minutes of the start of this motion, of this dynamical system. So 30 minutes, don't include 30. Instead, you need to include 1/2, which means a half an hour. So with that, when you multiply the speed with the corresponding time, 20 times, this is none other than 20 times 1/2, 20 miles per hour. Okay, so one half of a time, 1/2 hour at a speed of 20 miles per hour would result just 10. And at the same time here, 15 times 1/2, which would result 15/2. So those are pre-computed, and those are the two values for x and y that we will have here. So x should be fine and y should be fine. So pretty much like all the terms in the numerator are fine now. Z is the only component. Z is none other than, again, the Pythagorean, right? It's just the same thing for that particular moment. So let's include these two values in that picture, in that equation. Z is none other than the square root of whatever that summation. So once you have it, I'm going to just plug it in. This is Z. This is none other than just X. Y goes right. Oh, let me not do that. Y is none other than just what you see here. And then dx dt is what you have here. Dy dt is what you have there. Just plug them in the corresponding position to get the final answer. And it is not necessary to simplify unless it's demanded by your final form of the solution. So just don't overcomplicate it. All right. So the next scenario. Right. So, in fact, we do not need to move it anywhere. Let's leave it. Let's look at the situation. All right. 25 feet long ladder is leaning against a wall. The bottom of the ladder starts moving away from the wall at a speed of 2 feet per second. So the bottom of the ladder starts moving, sliding away. And in the meantime, the top of the ladder, of course, it starts sliding downwards. So the question is how fast it's moving, the top of the ladder sliding downwards over the wall. So to answer this, the starting step, first of all, variable x and y in this scenario, the graph or like the figure is given with variable. So it can save some time when the context is provided. And we know dx dt, that's also given. Dx dt is none other than the speed of the bottom of the ladder. And then x and y are none other than exactly the corresponding distances or corresponding positions. And then the length of the ladder is a constant, 25 feet long. So that simply means you do have Pythagorean right away, and then just differentiate that relation right at the beginning. When you do that, 25 square, whatever that number is going to be, it is 625, but it doesn't really matter. Don't even try to simplify. It's a constant. When you take the derivative, it disappears. So you do have that right away in the right side, and in the left side, you have 2x dx dt and 2y dy dt. That's the derivative of these two components. And then once you have it, all you need to do is to recognize dy dt. Therefore, I will leave this term on the left side and move this term to the other. When I do that, after doing that, 2 is a common factor that you can get rid of. That's what's happening here. And then to subtract dy dt, should be dy dt. We need to divide both sides by variable y. And then this is what we're going to end up getting. So it's all about recognizing these pieces now. The first step, dx dt is given, that is 2. So that's what you see here. Dx dt is just 2. And then how fast is the top of the ladder sliding down? Now, in this case, if you look at this very carefully, you may see something is missing because there is no information about variable x. In fact, that is a planned flow of this particular problem. I wanted to show you some missing information. When you have some missing information, you will never be able to get to the answer. So at this point, let me say, even with this problem right here, how fast is the top of the ladder is sliding down? I would say when the bottom of the ladder is 10 feet away from the wall. I need to have an additional condition. And now when I consider 10 feet away, that simply means the value of x is none other than 10. I can include that. And then how do you determine the variable y? That is coming from the same equation that we had right at the beginning. So to compute that, plug x equals 10. So it's going to be 100 plus y square equals 25 square, which is 625. In this case, I will just simplify it. Otherwise, you can simply have 25 square and 10 square here, and then y square is none other than the square root of 25 square minus 10 square. In this case, it's 525, and then y is none other than, okay, so y square, or like let's say y itself is the square root of 525. Of course, there are two values, plus or minus, when you take the square root. But we will just consider the plus because it's a length. And that is the value that we include right here. So once you have it, now the bottom line of this last problem is we need to have the correct amount of information. It shouldn't be more, it shouldn't be less. Now, in this case, there was missing information, and in that case, we cannot provide the specific answer. For the specific situation, specific scenario, we need to have specific data for the given situation. So that's exactly what we are going to conclude this lesson with. Now, most of the problems that you see in this setting, in this scenario of like related rates, and not going to be complicated. Like especially when it comes to problem solving, it will be much more easier than some of the examples that we discussed here. However, it is root in practice. Sometimes it could be challenging to build up some of these geometric relations unless you recall them. In such cases, you may be provided some supplements. Otherwise, when it comes to real world problem solving scenario, you may need to look it up, you need to find it, you need to investigate that particular scenario a little in detail. And that's exactly how you recognize the connections between variables. So it is a problem that is not only associated with calculus, but also in general to any math modeling scenario. More you know regarding the situation, more you know regarding the context, better you can express that in mathematics. So now, with that, we will conclude this lesson and we will proceed more uh, in the next lesson with more applications of the derivative. Until then, enjoy problem solving on this particular setting and have a wonderful time.